Okay, thank you. I'm excited to be here as a presenter this time. I've attended the 2000 Michelson interferometry workshop that was a precursor to Sagan, dating myself, and another one a few years ago. So I've always enjoyed these, they're great. And so just a quick overview, I'm going to talk about what we know right now with exoplanet observations, what are free-floating planets, and talk a little bit about the different formation mechanisms, and then sort of focus on how we can sort of probe the free-floating planet yields through the planet formation process, and I'll sort of cover both G stars and M dwarfs. Okay, so we've passed over 3,000 confirmed exoplanets to date. That's exciting. The majority of the large fraction of observations have been discovered with transits and NRV, but we do have some microlensing, as you all know. But if you look at the rapid growth of exoplanets over the past few decades, Eric Momajek was the first one to kind of notice this rapid growth that basically the number has grown exponentially over the last 25 years. And so I kind of stole this slide from Jessie Christensen that works at NXI, and it's a great graph. She gave a projection of what we are expected to find with both TESS in about 5 years and also with WFIRST. Many of these will be transiting exoplanets, and Ben Monte will be giving a talk about this bar here mostly, and a large fraction of those will also be microlensing planets, so it's a really exciting time. And so Kepler has discovered over 2,300 of the confirmed exoplanets, and, sorry. There we go. And I'm just showing this to sort of illustrate the diversity of multi-planet systems that it's found. You can see sort of to scale is the solar system terrestrial planets there. And so Kepler's found lots and lots of very short orbital period systems. And of the 3,500, over 580 are multiple planet systems. And if you sort of break it down, about half of these multi-planet systems have 3 or more planets, and the other half have 2 planets that are pretty widely separated enough that there could be planets within that. And so there are sort of two schools of thoughts about these different populations. One is that maybe planets form efficiently, and maybe in half of the systems they go unstable, and you end up with 2 planet systems. And the other thought is maybe they are all pretty efficiently packed, and we're just not seeing these exoplanets, either because they're too small or because they don't transit. They just need to be inclined by a few degrees for us not to see them. And so this is one of the outstanding issues with multi-planet systems. One of the big surprises from Kepler was that Jupiter-sized planets are pretty rare. We expected to see a lot of these, and we ended up seeing mostly Neptunes and super Earths. And so, going to free-floating planets, this isn't something that is sort of well documented as a population. Everyone shows all of these different microlensing surveys and transiting and RV survey results. So what is a free-floating planet? So I looked on Wikipedia, and it gave this full array of all of these sort of names you see in science fiction mainly, going from rogue planets to starless planets. And my least favorite is sort of Planemo, because it's planetary mass object. It's sort of in the same class as Tranit, transiting exoplanets, which I'm personally not a fan of, but it's just a matter of taste. And so a free-floating planet is a planetary mass object that essentially is orbiting the galaxy directly and doesn't appear to have a host star, as far as we know. That's sort of what I would consider a free-floating planet is And I took this, this plot straight from Wikipedia, because that's where you should get all your information. And so, as you can see, it's kind of there's a lot of sort of asterisks to everything. There really is only 2 confirmed planets, and I admit this is likely not up to date. But if you look at the mass ranges, you'll see that they're all very massive planets, and like Jupiter and more massive planets with a huge uncertainty range. And so most of these have been observed by microlensing surveys and optical and infrared wide field surveys. And so, so we know some of them are Jupiter, sort of Jupiter-class planets, but a lot of them might represent sort of the tail end of the stellar mass distribution. And so there's sort of 2 schools of thoughts on how these can form. One way is formation via collapse, and this is comparable to how stars form. Stars form by a collapse of a molecular cloud core, when basically gravity sort of exceeds all of the turbulent and other forces, and you end up with these stars and disks. And so free-floating planets could just be these sort of objects that form from sort of the same mechanism. The other way is through a process that's an output from planet formation. And so we believe that planets form in disks, and free-floating planets could just be a byproduct of this whole process, and basically be planets that were formed and then ejected by some mechanism. So the idea that planets form within disks is not new. We can date it back to at least Kant and Laplace in the 1700s. I'm very grateful to Caitlin for covering all of these different types of formation mechanisms, so I didn't have to do that much research in this last one. But essentially, there's all of these different models that have been that have been studied a lot. Primarily, core accretion is sort of the most widely known, widely studied model. Pebble accretion seems to be sort of the flavor of the year, and everything. There's been lots of dedicated studies for decades, and so regardless of which formation mechanism is your favorite, essentially ejected material is a natural outcome from this planet accretion process. And so some of the ways that planets can be ejected are through planet-planet interactions, as material orbits a disk and collides, and the planets sort of excite each other. Certainly, giant planet companions and stellar companions can dynamically excite material in the disk, and causing large enough perturbations to eject some of these. And external forces, so stellar flybys. Some studies have offered galactic tides as a mechanism, and even stars, while they're still in their birth clusters, could have enough perturbations in their environment to eject these things. And so there's a lot of analytical models, lots of numerical models that could essentially be its own Sagan workshop. And so I'm not going to go into depth about all of the models, but I do want to talk about numerical n-body models, because it's really a way that we can probe this sort of a formation of free-floating planets via ejection. And so n-body models are widely used tools in astronomy, and there have been dozens and dozens of studies that study formation around different star types and different stellar environments with different giant planet architectures. And so essentially these types of models where you look at bodies within a disk as they collide and accrete, you can follow their evolution and ultimately see where planets can form. you can see and try to understand the fate of mass that is perturbed into the star and do some stellar pollution models. And of course, you can look at the ejected mass that arises in all of these different configurations. And so some of the widely used integration packages to do these types of studies are Mercury and Rebound. Rebound's a nice Python-based one. And so they're all publicly available. Anyone can really go home and make their own planets today if you want and play around with them. So there have been some studies on planet-planet interactions that have been really interesting and have sort of probed the free-floating planet population for giant planets. Varus and Raymond did this nice study where they looked at, they performed a large suite of dynamical simulations, and they put forth this sort of simple but nice equation to determine basically if you know the observed frequency of free-floating planets from observations, and you can sort of try to estimate what number of planets you would expect that you would need to be ejected from a given system in order to match these observed constraints. So essentially, if you look at the frequency of planets, it is the fraction of stars with giant planets multiplied by the fraction of giant planets that become unstable and multiplied by the mean number of planets that are ejected via this instability. So they performed this large suite of simulations where they placed 3 to 50 giant planets in a disk around a sun-like star. In some cases, they used equal mass Jupiters. In some cases, they looked at a range of giant planets from Saturn to 10 Jupiter masses. And they looked at systems of giant planets that were spread out from 3 AU to 200 AU from the star. And they considered an ejection if one of the planet was perturbed beyond 10 to the 5 AU. And so if you look at their results, here on the left are the fraction of giant planets that were ejected for different numbers of giant planets that were initially in the system. And on the left is for their cases with equal mass planets. So essentially they found 10 to 30%, it's kind of a flat line, 10 to 30 or 40% of the giant planets were ejected. On the right, it's a little more busy, but if you just look at the blue line, again, this is for the unequal mass, giant mass cases. And because some of the larger masses perturb the smaller ones easily, they found that there's sort of a, you can eject more of the giant, you can have more of the giant planets ejected if you have a lot of more giants that are of different sizes. And so this is sort of a large window, but they found that you can have this this sort of constrain the number of giant planets that can be ejected in these types of simulations. So going back to this equation, so what they did at the time, their paper was out in 2012, and it was just after the SIMI results. And so when they plugged in the value of 1.8 as the number of expected Jupiters per star, and they assumed a 20% fraction of sun-like stars that have giants, and used their 70% fraction of planets that become unstable, what they found is that you would need every star to eject about 12 Jupiters in order to satisfy this observational constraint. And so what they concluded at that time was that this planet-planet scattering cannot alone explain the free-floating planet population. Of course, new results came out just very recently, and where this number was revised down to about 0.25. And if you plug everything in again, what you get is you would need 1.6 Jupiters to be ejected from each star in order to satisfy all of these observational constraints. And so 1.6 Jupiters is still a lot, but it's a lot more reasonable. So what about ejection of terrestrial planets? The same group, Sean Raymond and his team, looked at what would happen to the terrestrial planet region if you have these types of systems with different gas giant instabilities. And so in this study, he looked at this large disk that was sort of motivated by what we think the solar nebula, the primordial disk was for a solar system. And in the inner region, where you have the terrestrial sort of Mercury to Mars region, he placed a disk of embryos and planetesimals. He put 3 giant planets at Jupiter's orbit and a little beyond, giant meaning Saturn mass to 3 Jupiter masses. And in the outer disk, he placed a 10 AU wide belt of 1,000 planetesimals. And he placed these giant planets so they were moderately stable orbits, and evolved the system forward in time to see how many would remain stable, how many would be perturbed enough to have a giant planet ejected from the system. And of the 500 simulations he did, he found that in 2/3 of the cases there was a giant planet instability, where at least one of the giant planets was perturbed from the system. And so if you look at the mass that was ejected in all of those simulations, the red shows the distribution of ejected mass when the giant planets became unstable, and the blue shows when they did not go unstable. And you can see they're pretty comparable. 0.1 Earth masses is comparable to Mars's mass. And so essentially, there were many 1 to 2 Mars mass objects that were ejected, and just in a very few cases, a half or 1 Earth was ejected. And so having giant planets becoming unstable didn't really make a big difference on the mass distribution of ejected material. If you look at the time of ejection, then there was a difference. If you have instability in giant planets, a lot of the material is ejected early on. One thing that was interesting that I didn't show here is that giant instability does have a large effect on the material that gets pushed into the star. And so when the giant planets became unstable, a median of 23 embryos fell into the star versus 1 when they weren't. And so having these giant planets, which should be really destructive to the disk, really only affects what is getting pushed into the star and just some of the timescales. And so if we look at the radial velocity surveys that have a long enough baseline to observe Jupiter-like orbits at 5 AU, comparable to that, and look at all the transit results, we find that Jupiters are actually quite rare, around both sun-like stars and M dwarfs. And so then we have to ask, well, how does ejected matter change if you don't have giant planets? Because it could be that most systems don't have Jupiter-like analogs. I can dance.
I reset it at lunch. Sorry, Elisa.
That's I can do dance. That's okay. Okay. We'll have a 5-minute break.
Does anybody have any questions? Seriously?
Yeah, I could take a question.
I just want to know, what is the prospect, down to which mass can we detect microclimates in free-floating planets? Because you mentioned here terrestrial free-floating planets, so can we detect them?
So with W1st we'll be able to detect Mars-sized free-floating planets.
Free-floating mass.
Is that right? Yeah. Okay. Currently from the ground, I'm not sure what the limits are.
Well, the rest was a bunch of candidates, sort of point 1, point 5 days, which implies they, there could be 5%.
12 seconds. Okay. Ben.
When you say 6% of these stars head to Jupiter, how narrowly defined is the box that's Jupiter? The Jupiter at any separation?
Yeah, there. I believe it was 7 to 10 AU, or there was some constraint.
So not,
It's not what?
not hot.
Oh yeah. A Jupiter analog meaning an analog like an 11-year orbit, comparable to that. And the M dwarf result I took from your paper, so you probably know. Okay. Okay. Okay, and so we, with Tom Barclay and myself and a few others, decided to look at what would be the effect on the ejected abundance of material that would be ejected without giant planets in the system. And so we did sort of these typical n-body accretion simulations, which I won't go into detail, but essentially you put hundreds of bodies within a disk around a star, and you use these integration packages to follow the evolution as they collide and accrete, subject to gravitational perturbations from the star and from within each other body, and you sort of follow their collision until they grow into planets. And so we did hundreds of simulations with the sun and a disk out to 4 AU and a Jupiter and Saturn analog. And we used the exact same disk, and we did hundreds of simulations where we excluded the giant planets. We used a new model that includes fragmentation, so it's just a little more realistic. And we evolved the systems for 5 billion years. And I hope it's not too hard to see, but these are the results from one of our simulations. And so on the left, you'll see our initial disk starts at 0.3 AU out to 4 AU. Here in purple is Jupiter, and then yellow is Saturn. And what you'll see, the colors as I show this movie, the green represent all of the small sort of moon-sized bodies, and the blue are sort of the more Mars mass embryos. And red just means they're fragmented material. Oh, thanks, Don. Perfect. And on the right is the same exact disk and without any planets. And so you can see the time over here at 10 million years. We already are forming a system comparable to our solar system. We formed 4 roughly Earth-sized planets, where close to the ones, analogous to the ones in our solar system. What you see on the right is that even at 500 million years, we do still form a system of planets that sort of extended a lot longer. But what you see is all of this material that just hangs out for essentially the entire simulation. And without giant planets to, 1, kick out material from the disk, and 2, to excite the material to either accrete or do something, or get ejected, you just have this sort of mini Oort cloud that hangs out for the life of our solar system. And so without Jupiter and Saturn perturbing the system, we don't get anything ejected. Maybe a few fragments were ejected over 5 billion years. And so that's a problem if we are trying to form free-floating planets this way. And here's the same system without giant planets. And you can see at 2 billion years, everything is still bound. And so the types of systems that we form, so on the left are a handful of our simulations. Each simulation is on a row. And the top row shows what the solar system planets would look like to scale. And you see Jupiter and Saturn here. And so on the right are the simulations without giant planets. And so if you were to look within 2 AU of each case, the systems are statistically similar. Without giant planets, we form these systems of terrestrial mass planets even out to beyond 10 AU. And so I keep hearing that the Earth mass planets can't form beyond like a certain amount, but I think without giant planets, you certainly can. And also consider that the disk we're using only went out to 4 AU, and it only contained 5 Earth masses of material. And that was simply based on our solar system models. And so you can certainly have more massive disks, you can have disks that are extended much longer, and so you can certainly have a lot of systems of Earths, a lot more further out. And so if you look at the ejected mass in green, here are the simulations with giant planets. And this is the distribution of mass ejected. And so you can see that there's sort of 2 peaks, one where a lot of the smaller planetesimals are ejected, and then there's a distribution of 1 to 2 Mars mass bodies that were ejected. And we didn't eject anything more than 0.3 Earth masses in any of the hundreds of simulations. Simulations without giant planets, we just really ejected a few, as I mentioned. Okay, so why didn't we eject any Earths is the question. So if you just look at the top, this is sort of a chronology of our solar system. We think our star formed 4.5 billion years ago. The classical picture is that sort of Mars-sized embryos formed within about 3 million years. Within 10 million years, the gas in the disk dispersed, and so this is sort of the time when the giant planets have to form. And we think that Earth formed anywhere from 30 million years to 150 million years. And this is sort of this giant impact phase, where we have the moon forming giant impact is one of the, at least in our solar system, we think was one of the last final major impacts. And so then if you look at this lower plot that shows the ejection times of all of the mass, in green, again, are the simulations with giant planets. The dark green is simply just the more massive embryos. You can see that most of the mass was ejected before 10 million years. And so by the time you get to this epoch of when Earths are thought to form, almost everything has either been accreted or tossed into the star, and you don't really have lots of Earths that are really dynamically excited by that point. And then you just have hardly anything was ejected, except for on billion-year timescales, you'll get like an injection of a small fragment when you don't have giant planets. And so Tom used these results to sort of predict what W1st might see. And if you believe this classical picture of planet formation, then the conclusions are that W1st will find plenty of Mars masses, but very few Earth masses. And sort of the asterisk there is that that's only in the case if there are giant planets. If giant planets are intrinsically rare, then it's a different case. And so there was a study of pebble accretion simulations where they looked at forming planets in the same way that we did, but just with this different method. And here they show the distribution of mass that was ejected in the pebble accretion simulations. And so what they found is that they also form a lot of, or they also eject a lot of Mars mass material, but they also find that 1 or more massive Earths were ejected for every 2 Mars mass. And so this is an interesting result that is likely testable as well. There are some caveats with this. These were preliminary results from these pebble accretion simulations, and they admit that the simulations don't really reproduce the observed distributions well, and so should be taken with a grain of salt. But I expect to see more of these studies. Okay, so what about M dwarfs? M dwarfs are so important primarily because of the sheer abundance of them. We think over 70% of stars in our galaxy are M dwarfs. The typical microlensing host star is going to be an M dwarf. M dwarfs are going to be the types of stars probed by James Webb, and there's so many reasons why we should really understand these formation around these types of stars. So the problem in trying to model formation around M dwarfs is that the disks are difficult to constrain. And so if you look at observations, some millimeter wavelengths, and some other observations, sort of what the consensus is that disk masses should scale with star masses, and it makes sense. So essentially, as you go down to smaller and cooler stars, you'll have smaller and cooler disks. When looking at formation models, if you were to take the sort of typical, what we call minimum mass solar nebula, it's a disk that contains the minimum mass needed to form the solar system planets that we have now. If you were to take this disk model and scale it down to smaller and smaller M dwarfs, by the time you get to a star that's about a quarter the mass of our sun, you don't even have at least an Earth mass of material in solids left in the disk, and so that's a problem because we know of systems that have more than one Earth around M dwarfs. Kepler-186 is on the more massive end of M dwarfs. M dwarfs range from about 8% to 50% the mass of our sun. And we know that there's a system of 5 roughly Earth-sized planets around Kepler-186. And then on the other extreme end was TRAPPIST. TRAPPIST is a star that's 8% the mass of our sun. You can see how it's scaled by 25%. So it's this extremely tiny system that has a system of 7 Earths. And so that is weird. So studying planet formation around M dwarfs is really hard and challenging and so important. I think studying anything about M dwarfs is hard. But there have been simulations. Brad Hansen did a suite of simulations around a half solar mass star where he did not include giant planets. And he looked at a disk within half an AU, and his disk had the same mass that was comparable to our solar system. So it's basically a lot of mass very close in. And this figure just shows the distribution of the final number of planets. So he formed 4 to 6 Earth mass planets in the system. And plot on the right shows the distribution of mass. So he formed quite a few Earth mass planets also. But what he found is that even around M dwarfs, there weren't any planets that were ejected. So this whole system, even though it's very different to the ones we did for G-type stars, basically had the same results as far as ejected mass. And so we think Jupiters are rare, but there's sort of more and more evidence almost every week that is implying that Neptunes are likely common around M dwarfs. And so we saw earlier Suzuki present this sort of microlensing results where sort of the typical mass of a companion would be a sort of Neptune mass planet. There are also several M dwarfs detected by radio velocity surveys that also have Neptune and sort of more icy giants in these longer period orbits. And these are also appearing almost continuously. And so there's the strong evidence that, Neptunes could be quite common. And so we're sort of just starting a bunch of simulations looking at planet formation around M dwarfs because if we can put in a Neptune, that will really speed up our simulations because they take forever to run. And so we plan to really explore that parameter space and see if it really makes a difference. However, we do have some preliminary results for simulations that we did, again, in the solar system around a G-type star, where we looked at different types of giant planets orbiting the system. And so if you look at this dark blue curve, this is a system where we had the Sun and Jupiter and Saturn, and it's basically showing the total number of bodies as a function of time. So it's showing how much mass is either accreted or lost in the first early 5 million years. And so we saw earlier with Jupiter and Saturn, lots of mass is tossed right away, accretion is faster, everything forms within 100 million years. And then each of these curves represents different types of giant planets. So the purple curve shows what would happen if you had Jupiter and Saturn and decreased their masses by half. And then there's even smaller and smaller companions. This curve on the top in red is showing you what would happen if you have a 45 and a 15 Earth mass core in the place of Jupiter and Saturn. And so the reason I'm showing this to you is just to demonstrate that having Neptune in the system where Jupiter is sort of closer to the results of having no giant planets than it is to having giant planets. And so it could be, if it turns out the M-dwarf simulations are the same, it could be that Neptunes don't have a difference as well, and Neptunes aren't going to be contributing to the free-floating population as well. And understanding this for M-dwarfs is really important because, again, the sheer abundance of M-dwarfs in our galaxy. And so I just want to end by saying that really what is going to help all of these formation models is understanding the demographics of outer giant planet companions, whether they exist, what are their architectures, and also basically everything that W1st will provide is going to help out. Getting the demographics of outer giant planets obviously will help in our models, and our models can make predictions, and W1st is also going to be finding free-floating planets, so we can use all of these results to constrain our models. And so I think it's really exciting. And I'll end with that. This is a nice science fiction book and a movie about a rogue planet striking Earth. And so I was arguing that maybe we should be more concerned about free-floating planets and asteroids. Let's joke. Okay, thanks. I'll take questions.
We have questions for Lisa.
Can you comment on the rate of occurrence of like impactors and planetesimal collisions in the case where you don't have any giant planets or solar-type stars?
Yeah, so one of our motivations in doing all of these simulations is to really look at not just where we can form Earths, but to look at the flux of impacts that hit these Earths and see if they can form, if they can accrete water, and then most importantly, if they can retain water. When you scale down to M-dwarfs, the accretion times are a lot faster and impact speeds are higher, and so it's really one of the biggest challenges to habitability for M-dwarfs is retaining it. And so so that's the first thing we looked at when we did simulations with and without giant planets. And what we found is that without giant planets, you get slightly fewer impacts onto the Earths, but they happen on much longer timescales, so sort of on billion-year timescales. And so it sort of visits the question of whether Jupiter it was a shield to Earth. That's one of the, one of these, like, I don't know, things people always believe is that you need a Jupiter, otherwise lots of impactors would come and strip the Earth's atmosphere, blah, blah, blah. But it turns out that you get fewer because Jupiter's just ultimately excite the bodies in the disk and excite a lot of more material that has a chance of hitting harder. However, if you imagine that, we think Earth arose on, or life arose on Earth, 1,000 or 1 billion years after the start of the solar system's formation. Without giant planets, you will get without giant planets, you will get giant impacts on much longer time scales. So Earth would be at risk of, after 2 billion years of having a giant impact that could strip atmospheres. So it's that sort of, it's complicated.
A lot of the early simulations you showed assumed 3 giant planets between sort of Saturn and like really big.
Yeah.
And it seems like a lot of mass.
Yeah.
Am I worried about that? Is that a special case, or do we just not know?
I think we don't know. I think the idea for that one study was just to look at instabilities and how that would shape the terrestrial region. I wouldn't say a typical system will have 3 giant planets. It's kind of arbitrary. In fact, I guess that's what we'll find out with WFIRST, what that really is.